Functions and function notation. You're going to like this. Today we're going to work with a little bit of notation, just the basic premise of what a function is, how to write a function. Not a whole lot of mathematics in what we're doing today. It's mostly just procedural kind of things so that we're all on the same page for notation and otherwise. I want to make sure that you know what a function is. Not every equation becomes a function. Want to make sure that you can distinguish. There's really two types of algebraic equations. There's functions and there's relations. Now, a function is a type of relation, but I want you to be able to distinguish between the two. We're going to become familiar with function notation. I want you to be able to look at function notation and know what it means, and I want you to be able to take a function and be able to write it in function notation. Those are the three things that you'll be able to do after you do the assignment today. Did any of you, there used to be this thing, and every year the number of people who are familiar with this decreases because it seems to be gone. But there used to be, if you went to school during the era of Apple IIs, which probably is not many of you anymore, there used to be something called a function machine. It was, graphics weren't much in those days, but it had a couple of gears on the side that turned. It was pretty cool. And what it did was you could enter in any number, and it would put it into this function, and the gears would turn, kind of amuse you for a while, and then it would kick out a number on the output side. So this would be your in, this would be your out. So for example, you'd pick a number. Okay, Jeff, give me a number. 44. Okay, so you'd type in 44 and hit enter, and then the gears would turn for a while. It would flash some different colors, and then it would kick out a result of, say, 89. And you'd go, and you'd have to figure out what the machine was doing to that number. Okay? So, Brad, how about another number? 4. Okay, so 44 gave us 89. If we put 4 in, the output would be 9. And then you would, after each one, you'd try and figure out what the function machine was doing. And you'd guess as early as possible, and the sooner you could get it right, the more points you got. First of all, does anybody know what the function machine's doing to these two numbers that you picked so far? It's doubling it and adding 1. That's right. So our function would be, let me say that differently. Our output would be 2 times the input plus 1. And so you would type in that using x's and y's, and if you got it right, yay, it'd give you a new function, and you'd go on. But every so often, the machine would break down, and you had to tell when the machine was breaking down. Well, that's actually relevant for this reason. What is a function? This is related to the function machine. What a function does, it assigns to every allowable input value exactly one output value. Now that seems like a simple statement, but there's two very important pieces of information there. One word that's very important there is allowable. Because not every function will allow you to put in just any old number you want. Sometimes you're limited in your choices. Those numbers are called the domain. Now we're going to work with domain and range considerably more tomorrow, but we're just going to introduce the idea of domain here, and then we're going to kind of let it hang until tomorrow. Later on, we'll see why there are limits on the domain, or why not any value can be plugged into a function. The other very important thing about a function is one is that only certain numbers are allowed to be put in oftentimes, and the second thing that's very important is that the function will never kick out 2 values. If it does, your function machine is broken. At least that's what the game used to imply. So you can never, for example, up here, put in 6 and get out 13 and 15. If you did, it wasn't a function. There's another way to visualize that. Here's what you've got. Think about it this way. We're going to take a whole group of numbers over here. These are our input values. This is called the domain. Okay? And there's all these different numbers we can pick from in this domain. Out here are your output values. That's called your range. We'll work with that more tomorrow. But a function will always do this. If you pick a number over here, it will always send you to exactly one number over here. Now, from the criteria that are up there, would it be okay, would it be a function if it took two different number choices and put them out as the same output? In other words, would your function machine be working if you put in two different numbers and both gave the same output number? Yes, that's allowable. We could have a function machine that was programmed to kick out 1 every time, and it would still be a function. However, if you had one input value and it produced two different output values, could it be a function? No. That's what'll break the deal. It won't be a function if there's more than one output value. Okay, well, I'm going to give you a very simple example of a function here. Functions can take on many forms. They don't have to be algebraic equations. Here's an example of a function that's a set of 5 ordered pairs. Now, I'm going to ask you a very easy question. If I tell you the input to this function is 12, what would you conclude that the output must be? 1, okay? If I tell you 12, you say, okay, 12 is associated with 1. So the input is 12, the output is 1. If I tell you the input is 5, then you would say the output must be 0. If I tell you the input is 7, you say the output is... Can't do it. 7 is not in the what? It's not in the domain, okay? What is the domain for this function? What number of values are allowed to be plugged in here? -6, -9, 12, 4, and 5. Any number that's not there is not allowed to be put in. Okay? Now, does it meet the criteria of a function in the sense that it doesn't assign any input value to more than one output value? It does. Okay? Every number in gives exactly one number out. This one's not a function. Why? If there's two different values for one input, if I tell you -2, you say 17, no problem. If I say your input is 0, your output is 6, no problem. But if I say your input is 3, there's two different outputs. That's not valid. That is not a function. It's a relation. A relation will tie input and output values together with no restrictions. A relation isn't easy. Anything can be a relation, but it's a little bit tougher to be a function. Now, most of the functions that we're going to work with, though, are in the form of an equation. So we're going to look at a couple of equations now that are actually relations that relate x and y. We want to decide if they are a function. There's an example. That one is a function. Why? Pick any number on Earth. When you square it, if you plug a number in for x and you square it, will you ever get two different values when you square it? No. Then when you multiply it by 9, will you ever get two different answers? No. And then when you subtract 2, you still won't get two different answers. So no matter what you do, that process of squaring, multiplying by 9 and -2 will always give one answer. That's your y value, and that is a function. This one's not a function. Y equals 3x plus or minus 8. Well, what if I tell you x equals 1 in that bottom equation? Then y would equal 3 times 1 plus or minus 8. Well, what are the two output values you could get? You could get 3 plus 8, which would be 11, or 3 minus 8, which would be -5. There's two output values, so that one is not a function. No deal. That top there should say function versus relation. I made a mistake there, but it's not too important. Consider the relation y equals 4x to the third plus x. Now that's a relation. Anytime you've got x and y related, or any two variables for that matter, it's a relation. If they're related, it's a relation. Is that a function? Think about it. Is there any way that you could have more than one y associated with any single x value? Given an x, could you ever have more than one y that would satisfy that equation? No. That is a function. For any x value you choose, there will only be one y value that makes it true. But, I want you to look at this one. How about y squared equals x plus 16? For any given x value, will there always be exactly one y value? For example, x equals 0. If you let x equal 0, what does that equation become? Is there more than one y value that satisfy that? Yeah, there is. Don't you agree with that? Well, it could be positive 4 or negative 4. So when I say x equals 0, there's two possible solutions to that. Could be 4 or it could be negative 4, and either one satisfies the equation. Does that make sense? That is not a function. See, I told you the input, and if you can't all agree completely that there's one value for y that satisfies it, then it's not a function. A function means if I give you the x, you will all agree on y. But here, half of you could have said, oh, well, y is equal to 4. That makes it true because 4 squared equals 0 plus 16. That's true. But some of you could have said, oh, well, why not negative 4? Negative 4 squared equals 0 plus 16. That's also true. Okay? So since there was two values of y that work, there's two different outputs, two different answers. No, it's not a function. Okay. Now, we got a function there. Y plus 4 equals x minus 9. It looks pretty much like a relation right now because it's not clear what it's solved for. But there's a couple of things to note here. First of all, it's a function, and we could write that function as y equals x minus 13. You can do the algebra in your head there, all right? Subtract 4 from both sides. Y equals x minus 13. That is certainly a function. Now, a little bit of terminology here. We say that y equals x minus 13 is solved explicitly. We say that a function's in explicit form if it's solved for one of the variables. So y equals x minus 13, that is explicit. What does explicit mean? I mean, forget about math, for example. If somebody tells you to do something explicitly, what does it mean? Very specifically, okay? In a very certain way. Explicit means that the equation has to be solved for one variable. It is solved explicitly for y, or you could solve it explicitly for x. But y plus 4 equals x minus 9, that's solved implicitly. That's based on the word imply. What does imply mean? It means to convey an idea without necessarily saying it. Well, we've got a function in here, but is it spelled out for us? No, we had to solve it. So there's an implied function here, but we have to solve it to get it explicit or to clear it up. If you imply something to somebody, you're kind of suggesting it, but if you say it explicitly, then there's no question. Take a look at that function that's written up there. Just a little bit of terminology again. The function y equals 0.5x to the third minus 4x plus 7. it's solved explicitly, wouldn't you agree? It's solved explicitly for y, okay? It's solved for y. Solved explicitly for y. Now, a little bit of terminology. Would you be more likely to say that given an x value you could find the y? Or would you be more inclined to say that given some y value you could solve for x? You could do either one, but ultimately you'd be more inclined to say this function requires x to be plugged in and y to be the computed value. Okay? So that in general you would say that x is the independent variable. Independent means it doesn't depend on anything else. You can choose x to be whatever you want and it will kick out a y value. Y, we would say, is the dependent variable. That's the dependent variable because it depends on x. It's usually easier to remember what the dependent variable is because it depends on the other one. X is then, since it doesn't depend on y so much, we would call it the independent variable. And the other thing that you would say is that y is a function of x. Y depends on x. If we were to rearrange this mess and solve it for x equals boy, it'd be messy, some function of y, then we would say that x is a function of y, or x would depend on y. Yeah, yes. Yeah, you would. Gabe asked a good question. He said, what if this was 0.5x cubed minus 4x plus 7z? Then x and z would be independent. Y would be dependent, and we would say that y is a function of x and z. And we're going to see some examples of that in a minute. Well, moving right along, function notation. This is what we're going to spend the rest of the time on, is function notation. Suppose you have three functions, the three little functions. There they are. Y equals x cubed plus 16, y equals 4x minus 9, and y equals 4x squared. Right now, if I want to refer to one of those three functions, it's very awkward. Okay? For example, if I told you to describe the middle function, how would you do it? You'd have to say, well, it's the function that says 4x minus 9. So what function notation does is it names functions. It gives them names. All it is a naming system. So we would use function notation to distinguish. We assign each one of them a variable. Usually f is the most common one. We start with f and go through the alphabet most of the time. So we call the first one f of x equals x cubed plus 16. That's just the same as the top left one, but instead of y, we call it f of x. G of x is equal to 4x minus 9. That's the middle one. And h of x equals 4x squared. Now the reason that's convenient is I can say, what I'd like you to do is I'd like you to plug the number 3 into function h, and you know exactly which one I'm talking about.
Why can't you do f of y?
It's a good question. Amy asked, why can't you do f of y? Because, let's take a look at this. Y equals, that one is x cubed plus 16. Because if I ask you to evaluate this function, what do you need to know? What do you plug into it? Do you plug in x or do you plug in y? You plug in x. So by writing it this way, this is an indicator that our function depends on x. This is the one we need to know. And you're going to see why that's convenient in the very next slide here. If I asked you to find out what what the function f was evaluated at, say, 3, I just write a 3 in that spot, and we know that x equals 3. Just like this. F of x is equal to x cubed plus 16, and g of x is equal to 4x minus 9. Those should be the same ones as on the slide previous to this. We want to find f of 3. So f of 3, by writing f of 3, we're saying, all right, we're going to take f, which depends on x, and we're going to let x equal 3. So if we're filling in 3 in that spot, we fill 3 in this spot. So this becomes 3 to the third plus 16. 3 to the third plus 16 is 27 plus 16, that's 43. So f of 3 is 43. That's what function notation is. It's just more convenient than writing y equals because we can give them different names, and we'll often be working with more than one function. Same two functions, this time g of 12. Take a minute, figure out g of 12. So all we've said is, let's go to the function g, let's plug in 12 for x, and evaluate. 4 times x is 4 times 12 minus 9, that gives you 39. So g of 12 is equal to 39, that's all there is to it. Okay? All right. Now you can do that for any number of different ways that general principle can be applied. For example, same two functions, f of x equals x cubed plus 16g of x equals 4x minus 9. What is 5f of 2 plus 3g of negative 4? Well, that means we're going to take 5 times whatever f of 2 is and add on 3 times g of whatever g of negative 4. So the first thing we need to do is find f of 2. We did this a minute ago. F of 2 turned out to be 24. The reason that's true, to clarify, we had this up here before, but that's because 2 to the third power plus 16 equals 24. G of negative 4 is equal to 4 times negative 4 minus 9, and that turns out to be negative 25. And so then we have 5 times f of 2. That's 5 times f of 2 is, this is really just the value of some number. F of 2 we said already was 24 plus 3 times g of negative 4. That's negative 25. Equals 5 times 24 is 120 plus negative 75, 45. F and g are not variables. All they are names. All they do is name which function we're talking about. The f and g do not have values. All we're doing is saying that if we take the function f and plug 2 into it, that's what we get. Okay, but f and g are not variables. They're just names that clarify which function we're dealing with. Let's do a couple more, and hopefully we'll clear that up a little bit more. You're not limited to one variable. For example, f of ab equals 10a squared over b plus 5 root b. Evaluate f of negative 3, 4. Well, all we do is substitute in. What's playing the role of a here? What number are we putting in for a? Negative 3, right? A is the first parameter given. And so our function becomes 10 times negative 3 squared over b, which is 4, plus 5 times a, which is negative 3, times the square root of b, which is 4. Okay? And now we just need to evaluate that. So this becomes 10 times 9, 90 over 4, plus negative 15 times 2. Ninety over 4 is 45 over 2 minus 30. That becomes negative 15 over 2, or negative 7.5. So we evaluated at f, where a and b were the independent variables. The distance an object falls under the influence of gravity is given by d of at equals 0.5 at squared. So what's the name of our function here? D. D is not a variable. We can't ask, well, what's the value of d? All we can do is say that d is the name of the function. Now we can find out what the value of that function is when a equals 9.81 and t equals 3, and that's what we'll do. d of 9.81, 3.0 is just going to be plug in 9.81 for a, 3.0 for t. Then it becomes calculated work. 0.5 times 9.81 times 3.0. That 0.5 is an exact value. It's not really important right now, but if we round that off to 2 sig digs, you're going to end up with, anybody crunch that out? 44. So we can say that the value of d when a equals 9.81 and t equals 3.0 is 44. Here's another function, y equals f of x. We couldn't call it either one. We're going to y equals 4x plus 7, but we're going to give that the name f of x. So y is some function of x. It depends on x. First of all, it's important to note that that function can be solved for x. We can rearrange that. If we solve that for x right now, it's written implicitly or explicitly? Explicitly for y. Another thing to say is that we could say, is y a function of x or is x a function of y here? Nope. Y is a function of x. In other words, y depends on x. All right? We'll know what y is if we know what x is. But you could rearrange that. You could say, well, I want x solved. I want to solve for x. I want it solved explicitly for x. So minus 7 minus 7. Y minus 7 equals 4x. Now, still the same relation here. Is this solved implicitly or explicitly? Is it what? Now it's implicit. It was explicitly for y. This is still true, but now it's not solved for either one. So there's an implied function here. It's not clear, a little bit foggy, but let's keep going and divide both sides by 4. X equals y minus 7 over 4. Or in other words, as it's written up there, y equals 1/4 times y. Now is this implicit or explicit? This is explicitly for x. And would you say y is a function of x or x is a function of y? X is a function of y. Not every relation can be written as a function of x or as a function of y. But it's important to note that we called 4x plus 7 way back here in the beginning. We called that f of x. F depends on x, and that's 4x plus 7. Now, we could rewrite this as a function. We can't call it f because f is that function. So we can't call it the same name. You wouldn't have different kids and name them the same thing. You can't distinguish. So we can't call this f again. We'll call it g. But now, for this one, g is a function of what? Y. See, this function depends on y. So we say g of y is equal to y minus 7 over 4. Now that is equal to x, but we've given it the name g, and it depends on y. So we could start out with this, a function of x, and rearrange it to come up with a function of y. Let's do one more of those. That'll have to be it. Last one. 3y plus 6 equals 1/2 x plus 9. We want to write y as some function of x, and we want to write x as some function of y. Let's start with the first one. Let's find y as a function of x. That means we want to solve it for y. Let's solve it for y for the first one. So if we solve it for y, we can subtract 6 from both sides, and we get 3y equals 1/2 x plus 3. Could have done this in the last step, but let's clear our fractions and multiply everything by 2. And now we'll divide both sides by 6 so that y equals x plus 6 over 6. We're done. There it is. y equals x plus 6 over 6, so we can say that y is some function of x, and that is x plus 6 over 6. So we're done with the first question. We wrote it as a function of x. Now let's go back and write it as a function of y. 3y plus 6 equals 1/2 x plus 9. Subtract 9 from both sides. We're going to solve for x now. 3y minus 3 equals 1/2 x. Multiply both sides by 2. And we get 6y minus 6 equals x. Okay, we've got it solved for x, so we could also say here that x is equal to some function of y and we're done. We did both.